We continue with our lecture on statistical tests, and today the topic is about comparing two paired means. So, two groups where the observations are paired. So, a variable is measured in each subject before and after an intervention. So, that is an example of a paired data. Or when you measure something on the left and right eye, or when you recruit subjects in pairs and you match for the age, the postal code, or diagnose, or whatever. And when you recruit twins or siblings as pairs, or when you have a control and treated preparation in a lab and they are handled in parallel. So all this data, the observations are not independent. So when you make some measurements, for instance, let's say that you have the before and after, or the left and right eye. So these observations, they are not independent from these ones. So the independent analysis, like the standard student t-test or the Mann-Whitney test or so on, they don't know that there are correspondences. So if I tell you that before you had this and now you have this, before you had this, now you have this. So all these observations, now they clearly show that there is a decrease because of the treatment. So it is not that, for instance, we could have that this sample could have been paired with this one. So then, for some of the samples, for some of the pairs, you might have a decrease, but for some others, like the one I have told you now, you would have an increase. But if you have these pairings, then it is absolutely clear that there is a reduction caused by the treatment. So pair tests can exploit this information of what you had before and what you have after, or what you have in one of the twins and what you have in the other twin. And the difference is mostly because of the treatment. So these paired observations is a way of controlling many variables like the genotype, phenotype, the individual, if the individual is measured before and after, or left and right, or environmental conditions, because for instance in this laboratory experiment where you have two samples handled at the same time, the experimental conditions, the environmental conditions are the same for both samples. So actually the measurement, the true measurement, is not x and y, but the difference between x and y. You have to define a new variable that is x minus y, and for instance for this example, x minus y gives these differences, and you see here clearly that the differences, so you can are significantly away from zero. So you can compute the standard deviation with its confidence interval, the mean of these differences, and the standard deviation associated to the mean. And you see that these confidence intervals do not include zero, so you can safely reject the hypothesis that the difference between x and y is zero. So the confidence interval is constructed on the difference, and it depends on the usual issues like variability, sample size, confidence. So if the confidence interval includes zero, then the two groups are not significantly different. There is a very interesting example that Darwin, that the one of the evolution, measured the growth of 15 seeds of plants when they were cross-fertilized and self-fertilized. So he had the hypothesis that one of them would grow, the cross-fertilized would grow more than the self-fertilized. They would be a stronger offspring. Then the difference in growth was 2.6 inches, so the average height was this one, and 95% confidence interval was this one. So at the time of Darwin, all these tools were not available, but he reported his data, and then people afterwards have computed these confidence intervals. So the result was significant, but just by very little margin. So actually, the p-value of this experiment is 0.049. So it is, you would reject the null hypothesis, and but just by very small margin. And the problem was not that Darwin was right, was wrong with his intuition. He was right actually, but the problem was the sample size. So 15 seeds was a very little sample size to prove this small difference. He was just lucky with his data, and the p-value, he could reject the null hypothesis. At his time, there was not this tool, but he could have done it. But with a bigger sample size, it is much easier to show that there is a difference between these two groups. So the null hypothesis is that there is no difference between the two groups. And the p-value, just a reminder, it answers the question, if the null hypothesis is true, what would be the probability of observing a difference as large as this one, 2.6 inches, or larger? Then, so a difference as large or larger than the one I have observed in this experiment, that is the 2.6. So once you have done an experiment in which you have paired the data, you pair the data because you think that in that way you will control better the environmental conditions, the phenotype, genotype, and so on, or the individual intervariability. So once you have done it, how successful was that control? So you can try to estimate that in two ways. The first one is to estimate the correlation coefficient between the before measurements and after measurements, or cross-fertilized versus self-fertilized, for instance. And then compute the confidence interval and the p-value of the one-sided null hypothesis of no correlation. So for Darwin's data, for instance, the correlation coefficient is minus 0.33, which is rare because you do the pairing because you think that these two measurements are correlated. And what he found was that they were uncorrelated. But actually, the confidence interval, we are not reporting here the confidence interval, but we are reporting the p-value. So the p-value is relatively large. So that means we cannot reject the hypothesis that there is no correlation between the two data. And actually, if you analyze another way of checking whether the pairing was successful is to analyze the data, but now in an unpaired fashion. So you do the paired comparison, you do the unpaired comparison, and you compare the two results. And the p-value for Darwin's data was 0.02 if it is analyzed unpaired. So actually, it would be better for this particular dataset to do the unpaired analysis than the pair analysis. And the reason was that he was unlucky with his sample, and then they were slightly negatively correlated, not too much and not enough to be significant, but he was lucky with his sample. And the assumptions of all these comparisons is that the samples are random, so they are representative of the population you want to extrapolate to. Then that the pairs are independent of other pairs, so within the pair they cannot be independent, but each pair should be independent from the other pairs. So the value that you observe in one pair should not affect in any way or should not be correlated in any way with any other pair. The difference between matched values follow a Gaussian distribution. So all these paired analysis, especially the paired t-test, if you do a non-parametric paired test, then this is not true. Then there are variables that you have to treat or pre-treat before doing any comparison. For instance, let's say that you do some measurements and you do a control, so before measurement, so before applying the treatment and after applying the treatment. So, and when you plot data, this is what you have before, this is what you have after, and what you see is that the larger the response that you had in the control, after the treatment, it is even larger. So for here there is an increase, but the original value was relatively low, and then if the original value is high, the increase is much bigger. So that calls for a logarithmic transformation. So if you see these kind of lines that are diverging, so after doing the logarithm, the lines become parallel. So that means that there is a change that is multiplicative rather than additive. So you have to do the logarithmic transformation before analyzing the pairs. So before doing the pair comparison, you should always make this kind of plots of the pairs just to see if you need to transform the data in some way. Then you can also do paired analysis between binary variables, and this is called the McNamee test. So pairs are like always, so these case control studies where you have an individual and then you have a matching control, and they are matched on age, gender, race, and whatever other variables you think they make sense. Or you make studies with twins, or you make a measurement before and after applying a treatment. And the outcome of all these studies to apply the McNamee test, they have to be a binary variable. So could be, for instance, the absence or presence of some characteristics. For instance, let's say that you want to see if a drug helps to reduce the prevalence of a symptom. So, for instance, a running nose with a cold. And for a number of people, we measure the effect of the presence of this running nose before and after giving the drug. So what you have is before, how many people. So you divide the observations in 4 categories. So the first category, you count how many they had running nose before and running nose after. And the second category is how many had running nose before but they don't after. And then how many didn't have running nose before but they had a cold. So they didn't have running nose before but they have after, and they didn't have and they still don't have. Okay, so this is a contingency table, but it is not a standard because in the standard contingency table the measurements are independent, but here somehow the individual is the same. So it's the same individual that has a running nose before and after, or so on. And so some mistakes when doing paired analysis. This is a common mistake in general in data collection. That is, when the result is almost significant, statistically significant, then you collect more data to increase the sample size and to recalculate the test. The problem with that is that you are doing multiple testing and you stop as soon as the difference becomes significant. And maybe if you continued further, then you would be back to the non-significant region. And because the p-value is such an unstable measurement, you might just by chance fall into the significant region. So if the experiment has 3 or more treatments, you use the unpaired test to compare two groups at a time. So the right tool to do that is the repeated measures. Repeated measures is the one that in which the individual serves as control. So let's say that you measure the same individual at time equals 0, then after 1 hour, 2 hours, 3 hours. So that the individual is the same, and you can calculate what is the contribution of that individual to the observations, and that is the repeated measures. And then you have repeated measures ANOVA and the postdoc analysis. The postdoc takes care of these multiple comparisons and comparisons of between groups. Then another mistake is not to do a transformation when you should. So if you have a multiplicative model for your data, like this one, that the larger the response at the beginning, the even larger it will be afterwards, then you should absolutely take a logarithmic transformation for that. And not doing a transformation when you should also biases your analysis. Then analyzing the absolute value of the differences instead of the differences. So all these tools like the t-test and all these things that we have seen here, they are thought for working with the differences, with sign, not with the absolute value of the differences. Then another mistake is deciding pairing the data only after seeing the data. So this is data snooping that you know that you shouldn't do. That is taking decisions on how to analyze the data once you see what is the output. And the reason for that is that it might be that the observation that you are doing is just by chance, and then taking decisions on analysis by a chance decision is not a good idea. So comparing paired observations is really very powerful to remove the inter-individual variability. So for instance, let's say that you're comparing hands, or you're applying some treatment on hands, so that there could be a huge variability between individuals. But if you make that the same individual serves as its own control, then you're removing a lot of variability, and then you can concentrate on the change induced by your treatment. So this is all for today, and see you next time.